All right, so we've got 5 points or currents you need to identify here. All right, let's go after. I look at a titration curve. I look at the most obvious points. Okay, so for me, okay, I look at this and I have the wrong colors in my hands. For me, I look at the equivalence point. Now this graph should look a little different than the graph that we just got, or we got from reviewing our acetic acid titration. What's the difference here? It's got a smaller asymptote, and this is also part of what I'm trying to teach you. Okay, so party people, okay, when we did this titration the other day, all right, what do we have here? We had, not that, we had something that was what? Started low and went much higher. And I can thicker that up. So we started something low here and we went much higher. And if we had a strong base, remember, it was like stayed low for longer and then shot up. So what I'm showing you, here's a strong acid, here is a weaker acid, and here is an even what? Weaker acid. What do the final line always show you? If we kept adding 25 liters of all of that strong base, won't I eventually approximate, get to almost the limit? If you ever done any mathematics, I'll never get there, but I'll get pretty close to the initial concentration of the base. Right. Now, what was the Ka of the acetic acid? You know, it was like, oh, I don't have this right, so 1, 2, 3, 4, 4.5. Okay, it was the pKa. This one's going to be what? Even higher. So as the pKa jumps, that's going to tell you your what? Your Ka is smaller. pKa is the what? The result of making a negative exponent positive. Remember, pKa is the negative log. So think about it. If I have 1 times 10 to the negative 10, okay, what's my negative log of that? 10. So as my pKa's get bigger, my Ka's get smaller, right? That's what we're showing here. So as my acid gets smaller, the asymptote is less sexy. It's not big anymore. Not that being big is sexy. I'm not sure, but I should get away from that. The point I'm trying to make, maybe it is, all right? I don't know. It's all a thing, and I should move on. If I just moved on, I wouldn't be stuck in this awkward moment. So let's make it a 5-minute spiel. No, but the point is, the reason why the asymptote is small is because we didn't start from a stronger acid, and you need to realize that. This is going to start to level up. What if we were titrating the base with itself? Wouldn't it be a straight line? Right, so as the acid gets weaker and weaker, okay, that happens, and I wanted to show you that. But let's get away from all of that. Okay, so let's go attack the points. So here, graphically, all right, now graphically, I notice that I'm kind of, and again, this is an estimate always from the data table, but we can still do some good stuff here. So if I look at this kind of area here, all right, the middle of that, I'm going to guess, and we could come to different agreements or disagreements, but I'm going to say it's starting to turn up here, and it kind of is turning up here, and the halfway point, I'm going to make this point right here my equivalence point. Okay, now you could probably guess a little bit above or below, but that's my equivalent point. What point is that? We're going to make that always 0.4. Okay, so that's going to be 0.4. Obviously, we have 0.5 over here. Okay, and as let's go through this. Okay, 0.1 is the initial. Now you should have realized, party people, that the initial pH, okay, was much higher than we've had before. Hey, it's a weaker acid than we've dealt with, correct? So the pH should start pretty high. This, of course, is 1. Okay, 2 is going to be the half equivalence point. Now let's go find that volume. Okay, so I know that I'm starting kind of here, here, so about right here is my equivalence volume. So we're going by 2s, 22, 23, 24, 20, did I mess that up? Looks like I did. Oh my gosh. Okay, so what is that value? Is that 27? What is this going by?
2,
4, 6. I just can't do math, I guess. I don't know my 2's very well. 2. Okay, I'm nervous. 2, 4, 6, 8. Okay, I can do this. All right, maybe I can't. All right, so anybody watching saying just turn this off and go to someone else. All right. So any case, that's 22, 24. I'm like 26, 28. So we're about 27. Let's call it 27. And again, if we're off by a little bit here, there's wiggle room because it's supposed to be an asymptote. So I'm going to say 27 milliliters is my equivalence volume. Good enough estimate. All right. That's my first attack, is I find my equivalence volume. Now, once I have 27, hey, what's half of 27? 13.5. Now, people are going to help me with this, right? Because I really messed that up. That was 12, right? This is 14. So this must be 13 and 13.5. So should I be right here? Oh boy, I did it good. So 13.5, okay, is going to be my half equivalence point. And that's course number 2. That's important. How did I do that? Once I found this equivalence point, I figured out that that's the volume. What was this value? 27 milliliters of the base was enough base to completely neutralize all of the ammonium ions, that weak base. So the half as much would be half that. That's important. Now, you can't identify number 3 unless I tell you which point we're going to look at. Okay? So I'm going to tell you, let's identify at 22. So I'm going to tell you that this is number 3. You could never look at this on your own and say, which point do I take? Remember, what's the buffer region? Let's do this. The buffer region, let's change the color because it's fabulous. Okay, make this bigger. The buffer region is where? I should do that, Begratsky. It's a little bit right after. This is the buffer region. Right up into that point. So I can give you, now I shouldn't have encapsulated this point here, but anything above 0 but less than equivalence is a buffer region. And what do we know about the buffer region? To get a point there, what can I use? Henderson-Hasselbalch, right? Okay, cool beans. All right, first and foremost, some skills that we should definitely have done, or at least know. We should know the net ion reaction. Okay, that should be written. So what's the net ion? Oh, Christmas, that's not going to work. The net ion. I say it twice because I'm stalling. Okay, so it's going to be NH4 plus, okay. Now, this is the driven reaction. We know other reactions are going to occur, so what's driving this weak acid? And we know it's a weak acid. Look at its pH. It's like 6 point something initially. Ooh. So, what do? We know it's plus. OH minus is going to drive it forward. Why don't I put the chloride ion? Because it dissociates in water. It's a wetting that we talked about. And of course, it's a chloride ion over here. We get rid of the spectators. And what does the hydroxide do? It pulls off an H, and it makes the NH3. We should recognize that to be the conjugate what? Conjugate acid, conjugate base. Conjugate means same chemical. And of course, you just made water. That's a driven reaction. That is a completion reaction. As much hydroxide as we add, we pull this thing along. You need to understand all titrations are done like that. Okay, second thing, that's the first thing we need to do is the net ion. Boom, that's done. Now, the second thing is, hey, what's the concentration? What is the concentration? Don't forget, and sometimes it's really helpful to draw this. That's why I'm kind of giving 2 boards here. Okay, what's happening is we have a... Well, it's making a comeback. Okay, now in here, what do we have? We have, some colors going. We've got, okay, the solution's blue, like all solutions, right? All right, so we have NH4 plus. Why drew an N? Not really sure. I need help. Okay? And we are adding drops of what? Jupiter. Okay, that have what? Okay, my base wasn't red. Okay. And of course it's a hydroxide ion. And this comes from the burette. Okay. All right, so we dropped it there. And we know that this solution in the burette, I know it wasn't red, was what? 0.10 molar NaOH. That's my standard solution. What's the point of a titration, people? To answer something about what you have, and know to answer something you don't know. So we want to answer about the concentration of the, look at the brackets, concentration of NH4+. So what are we going to do here? Okay, well, the first step is identify the equivalence point. Well, we have done that. Second step is for me to find my Apple Pencil. There it is. Okay. Third step is continue on. So I found that 27 milliliters. So party people. All right, so I'm going to do this right here. You can do this any way you like. You can find space. Oh, so I can get bigger and smaller, and you can't. Ha 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 ha. Okay, so. Okay, so what was the volume at the equivalence point? 27. So we had 27 milliliters of hydroxide that was added. Party people, this link, I want moles of hydroxide. How many OH minuses were dropped and needed? The equivalence point is telling me what? It took 27 milliliters, and I'm telling you that the base that we used was 0.10 molar. So convert this to liters. So 0.07 liters. Volume times what? Molarity gives you what? Moles, as long as I write the molar compound. So you should know this. Okay, so I can do this in my head. Point was always dangerous, going in my head. So 0.0027 moles of what? OH minus. What do we know at equivalence? That's the point where all of the hydroxides equal the what? Let's put it this way. The protons that come off the NH4+. So it equals 0.0027 moles of the H pluses that were removed by the strong base. Forcibly removed. Get out of there. All right? Now, but I want to solve the concentration. I'm almost done. I got, what's molarity? Moles. Hey, I got that. Over what? Liter of solution. Total volume, right? I added 27 milliliters, so I got to add that to the beaker, right? Wrong. Okay, party people, we dropped 27 milliliters to find a certain number of moles of this. I want to know the concentration. Point one is the concentration, or part of part one is the concentration of the initial beaker. I want to know what the concentration after I add 27 milliliters of hydroxide, what's the concentration of the extra H pluses? 0. I want to know the concentration of H pluses before I add. Yes, I have to add 27 and read from the graph. What am I doing? I'm figuring out 27 or 0.027 liters of this is equivalent to what's in here before I do anything. So that's the hard part. I'm using the initial volume, which is 25 milliliters. So 0.025 liters. And so we've just conquered one thing. 0.0027 divided by 0.025, very close to 0.1. That's what I was trying to make. Okay? And so what I get here, party people, is 0.108 molar. And that's the concentration of my NH4Cl. Or my NH4+, that's a 1-to-1. People start putting the total volume. No. You used that much of the base to figure out how much moles is in the beaker, and then I want the initial concentration, so I use that moles divided by the initial concentration. Okay, 2 skills done. We haven't done any points. So let's go on. Okay, let's go to the first point. But I may have to go back and forth. The first point is I want to verify the initial pH. Okay, so what do I know? Well, party people, I know something about the first point. The first point, I know that it's not a strong what? It's not a strong acid. Okay? So I have to do equilibrium here. But if I don't recognize that, let's write the reaction. Okay, so what's happening here? The reaction is just like this. We're going to have in this beaker, before I add any base, aren't I really going to have NH4 plus? Plus who? Just sitting in water. And this is going to be equilibrium. Why? Because it's not being driven. I haven't added any hydroxide. And what's going to happen is some of it, not much, but some of it is going to become NH3. And some of it's going to become H3O plus. Synonymous. So there is our equilibrium. It's a new reaction. Mr. Grosky, we didn't write that reaction because the titration that occurs on the curve, we haven't started here, is we drive it. But here is just sitting in water going back and forth. You guys saw its initial pH was what? 6 point something, pretty high, weak acid. So we need to solve for this. We need an ice table. And what I want to solve for, party people, is I want to solve for the concentration of H3O plus. So initially, now this is a what? This is a equilibrium problem. What goes in an equilibrium ice table? Molarity, because it's related to equilibrium KSPs and KAs. And you notice we're going to need that, aren't we? So we're going to stop somehow, but we'll get back to it. So initially, how much NH4 plus am I starting from pure zero? What was the molarity that we just found? 0.108, so I put that there. Okay, we don't care about the water, it's a liquid. Okay, and this will be what? 0 and 0. We're starting as assuming all of this has its H plus. I know it gives up some. We're going to start from the 0 position. And it's going to come forward. Now this is going to be minus X. This is going to be what? Plus X. And again, at some point, guys, you won't need to do this. This is 0.108 minus X. And this is going to be X and X. And so, what we're going to do now is write the equilibrium expression. And what would that be? Okay, well that would be Ka is equal to what? Okay, right, let's just make it fast, but these are X's, right? Products over reactants, right? So X times X is X squared, right? Let's go right to it. Over what? Right, products over reactants. So this is going to be 0.108, and I'm going to get rid of the minus X because Ka is so small. Before I can solve it, oh, I need a Ka. So I got to stop my work on 0.1 and start looking at 0.2. And this, my friends, 0.2 is going to help me solve for the Ka that I need for 0.1. I know, it's crazy. So we look at 0.2. What are we thinking here? Let's look at here that this is 9. So I'm seeing a 9.4. Or for me, it's 9.4. So I'm going to say 9.4. And what is that? It's my pH, right? I'm not going to do the Henderson-Hasselbalch, what? Derivation every time. What do I know? pH equals the pKa. So party people, I find that pH. Booyah. Skill number 2. So what I find is the pKa. Let's go right over here. I'm going to change colors because I can. The pKa, I said was equal to, oh, my short-term memory is gone at this height, 9.4. I know you said too much. All right. Cool, but I need the Ka. What does little p mean? Puny. No, it means that's the negative log. It's actually the what? It's really 1 times 10 to the negative 9.4. That's what the actual number is. Right? So what we're going to do is do 10 to the negative x. 10 to the negative 9.4 to find the Ka. And let's do that. Okay? And I had a later of calc in front of me somewhere. All right, so here we go. So we got, okay, so yes, that's the, it's the inverse, it's the opposite. So I do second function, no, just, yeah, second function, 10 to the negative x, I'm just going to do negative 9.4. And party people, I get a Ka equal to 3.98 times 10 to the negative 10. Hey, that's a small Ka. And that should make sense that we're going to barely go forward, right? So the x that we take away from the 0.108 is insignificant. So back to reality. I'm going to get rid of the Ka. I'm going to put in my value of 3.98 times 10 to the negative 10, whatever you get. Now, of course, to solve for this, I have to times it by 0.18, so times it by 0.018. To solve for my x, I square root my heart away, both sides. So I take the square root of both sides. Second function, second answer, here we go. And I take and find my x to be, or not to be, is 6.56 times 10 to negative 6. Now what is x? Woo! It's H3O plus. How do I get a pH? Negative log, party people. This is not so bad. So negative log of that concentration, second answer, close the parentheses, and I'm supposed to get 5.18. Now, we have some error here. I'm supposed to get 5.18? And I got way over 6. I'm supposed to be here, okay? It's a little bit of an unverified point, but remember, we're dealing with pH probes. I did try to calibrate them, all right, but they do have some error, okay? So, and also, the Ka I'm using is right off the graph. If I was to use the known Ka, I could also do that probably a little better, but it's all good, okay? It's all good. All right, so, but that's verified, or at least that's what I want you to do there. So that's 1. 2, we're done. 2 is about what? Now, in reverse, how would I do? Remember, we're going to do this forward, and next week go in reverse. In reverse, how would I do this? How would I find this point? I'd have to give you the initial concentration of the beaker. Okay, then you would do that. And this way we had to solve for it. In the reverse, how would I get this point? But I'd have to give you the Ka, the acid, and what would you do? Negative log it to get the what? pKa, and then once you know this point at equivalence, you just do half. So that's, understanding the forward is understanding the backwards. Now 3 I'll do last. Now let's do number 4. 4 is like the homework. Let's solve for the pH that we're supposed to be at equivalence. Now, what is 0.4 at equivalence? This is where the what? Hydroxides equal the protons in the beaker. We drove this thing 100% forward. Look at here, party people. We drove this thing 100% forward. So as many moles of NH4 plus I have here is the same moles of this. Ooh la la. So how many moles was that in number 4? Did we find those moles? Look at this. I have it right there. Okay. So what am I going to do? Can everyone realize that's going to be the moles of the conjugate base? Do I have to draw a stoichiometric table there? I was showing you last night. Look at the ratio, guys. It's a what? 1 to 1. At this point right here, it's kind of having a limiting reagent for both of these. So as many moles of this equals that at this position, and we have wiped away all of the NH4 plus. So whatever moles are here that was minus, this is the same. So the moles of the hydroxide or the H plus is now the moles of the ammonia. And if you weren't with me last night or didn't dive into this, I showed you that. I'm not going to break it all down again today. So right now, I drove that forward, and the moles of OH is 0.0027, but that's equal to the what? Moles of the conjugate base. All of the conjugate acid is this. And every single one became the conjugate base, so they have to be equivalent. So that's 0.0027, and that's moles of what? Conjugate base, which is NH3. Okay, party people, we've got a new equation. Because at this point, we no longer have acid. We don't have any more of the weak acid. We don't have any more of the strong base. What we have now is the base, the conjugate base, sitting in what? Water. And this is not going to be driven, is it? No, what's it going to be? It's going to be in equilibrium, reforming a little bit of the conjugate acid. And it's going to make, if you notice, some hydroxide as the H is pulled. Okay, and that's why what? The equivalence point is way above 7. But we want to know what the pH is there. What is the pH at that point? So here comes an ice table if you have to. Okay, now this is a molarity. This is an ice table. So party people, this 0.0027 moles is inappropriately used there. I got to divide by the what? The liter of solution. At this point, how much volume of base was added to the beaker? And how much was in the beaker? So at that point, we have what? 52 milliliters. So I'm going to make myself a molarity here. 0.052 liters. I'm going to go find that number. 0.0027 divided by 0.052. And what I get, party people, is I get 0.052, we'll call it. It doesn't make any sense. How do I get the same number? Did I do that right? Did I do that right? Okay. Yeah, I can because of that. Okay, I just a little math fun there. Didn't have any. So I had Christmas in July. 0.052 molar. You with me? All right. Now, I don't care about the water. It's a liquid. Okay. Let's change this up with a color because I can. And we're going to assume we have what? 0 of that and 0 of that. And what do we know? Hey, this is going to be minus x. It's going to go to what? It's going to react with water to go forward somewhat. Okay, and guess what? This would be plus x. This is plus x. This is x, x, and this is 0.052 minus x. You can guess. You're going to get rid of that x away. But this is right. The KB now. So the KB is equal to, for the millionth time, x squared. All acid and base reactions become x squared. They all become 1-to-1. Over the what? The concentration, 0.052, right? So we need the KB. So what do we know? Ka times the KB equals Kw. To solve for the KB, it's the Kw divided by the Ka. We found the Ka, didn't we? Right? Is that right? Yeah. Kw is 10 to the negative 14. That's the equilibrium constant of water dissociating. And what I say was it was 6.56. Is that it? No, that's X. Oh, 3.98. 3.98. 3.98 times 10 to the negative 10, right? Put this in our later of calc. Why does he say that? He's very tall. Okay. Negative 14 divided by 3.48 second function e to the negative 10. Sounds like foreign language there. If I did this right, I got a KB equal to 2.87 times 10 to the negative 5. We good there? Did I do that right? Okay, so people are believing me. Always a problem. Okay, if I say so. If it's close enough,
Yeah, I got you. But I think you did 3.4.
I could have.
It's
I
okay.
did. So what did you get?
2.51.
2.51. You're right. I look at my calculator. Guys, supposed to stop me. 2.51. All good. Okay. So 2.51 equals this. So that's easy. You're going to times that. 2.51 second function e to the negative 5. I'm going to, oh, Christmas. Just 2.5 second function e to the negative 5. And I'm going to times that to 0.052. And then I'm going to take the square root of both sides. Second answer. And I get an x equal to what? Yeah, 1.14 times 10 to the negative 3, right? And that's my what? That's my hydroxide. So let's go get let's get a POH. Negative log of that. So simple now. And the negative log of that is 2.94, but that's the POH. 14 minus that. And we get a pH of 11. Now let's see. Are we somewhat close? Yeah, this one's better. So we should have a pH of 11. We got something bigger. So we verified the pH there. All right, so let's go after, we've done point 1, we've used our point 2, and we've just finished point 4. So let's go on to point 3. So we have our 5 points, and what we're going to do is we're going to solve now for the third point. Now when you do a titration curve, okay, obviously I call this region the buffer region, and I'm going to tell you which point. And in this case I'm saying let's pick point where the 22nd milliliter of base that was added. Let's go see if we can verify that point there. Okay? Now of course we can do it a couple of different ways. We could do equilibrium. So to get to this point, all right, and this is really important to get to this actual pH, starting with a concentration of ammonium ions, which is a weak base. Weak acid. Okay, we adding a strong base to drive it forward. Okay, and so these pH changes to get to this position, the hydroxide is driving the weak acid forward. And at this position here, okay, what is the pH? Well, that pH is a function of the H pluses that are available in equilibrium with water. So how much acid do we have remaining? So remember, to get to this position, we're going to drive the reaction forward. If you notice, this is the equivalence point where the H pluses from the ammonium ion equal the hydroxide that's yanking them, okay? Remember, this is reluctantly giving off an H plus. The hydroxide is stoichiometrically. What I mean by that is for every one of these is grabbing an H, okay? No one's left unaccounted for. But in this position, because we haven't gotten to the point where there's an equivalence point, this is the halfway point. Remember, this is where you have 100% conjugate acid. Here's where you have 50% conjugate acid and conjugate base. That's that max buffering position. That's the position we can get the pKa because the log of those two values is 1. And this is where you have 100% conjugate base that we just did. So if we're at this position, we drove it forward, we created something called a buffer. And that happens a lot in many of these questions where they're going to give you a titration, but they're not going to titrate all the way to the equivalence point. They're going to titrate to some position, okay? And why would they titrate to some position below the equivalence point? To create a buffer, okay? Now, why would you want to create a buffer? Now, what's a buffer? A buffer is you have some conjugate base, some amount, and some NH4+. As we've learned, this position I call the max buffering position because this is where you have equal amounts of acid, and conjugate base, meaning that you can actually prevent swings of pH. That's what a buffer does. It prevents huge changes of pH. If I have a buffer solution of equal amounts of ammonium ions and NH3 and I drop some acid, hey, the base part can absorb some of that and keep the pH pretty constant. If I drop some base, the acid part could neutralize that and keep the pH constant. Eventually, as you run out of one of these two, the pH swings. So I call this max buffering because we're at this position where we can buffer equal amounts of the acid or base that's added. But as we go this way, we're tuning our buffer to have a lot more what? Well, as I drive it forward, this is 50% conjugate what? Base and conjugate acid. As we get here, okay, now it's going to be more conjugate base than conjugate acid because eventually here, it's 100% conjugate base. So we might go 50, 60, 70, 80, 90, now 100. So here we have a lot more conjugate base than conjugate acid. But the point is, to drive it that way, all right, we're going to have some acid remaining. Right now, we know exactly how many moles of acid are in our beaker. Okay, we found that out. Okay, let's write that so we understand. We did that initially using 0.1, and that value was what? 0.0027 moles, right there. Okay, and we solve for that, and that's how many moles we have, okay, in the beaker. That does not change. This represents down here the volume of base that we're adding. So if we're stopping at the 22 milliliter mark, I'm making that 0.3. We didn't add enough base to neutralize that. So the amount of moles added is less, which means there's going to be some acid remaining. So once I stop, do a partial titration, and leave the titration hanging in balance right here, obviously we kept going, but if we left it right here, we would have a buffer, both conjugate base and conjugate acid. There'd be some acid remaining because we didn't add enough what? Base to drive it all the way. At this position, we've added enough hydroxide. I'm looking for the reaction. We've added enough hydroxide to drive it completely forward. But at this position, okay, we didn't add enough hydroxide. There's some less amount. There's moles that is less than 0.0027 there, okay? And so we want to figure out stoichiometrically how many moles of acid is remaining, all right? And then I could come up with a molarity of that, and then what I could do is I could do an equilibrium problem and see how far forward this reaction has to go, okay? And we could do that, and I show you that in my notes. And that becomes cumbersome. A better way to work with any point that's just above the 0 point and just below the equivalence point, okay, this buffer region, is use the Henderson-Hassel lock. That is the best way, the fastest way. You don't have time. So we're going to do that. But before we do that, I have to evaluate my moles here. So, just as I showed you here, that's how many moles of hydroxide is in the beaker. How many moles of hydroxide is added at 0.3? Well, at 0.3, as we just said, it was doing 22 milliliters has been added. So party people, let's go find the moles at 22 milliliters. All right, so without further frost, let's continue. And I'll use a new color because I can, maybe. And so what we have is Christmas, not that. All right, let's go 0.10 molar. As I said before, the molarity times the volume is equal to what? Well, is equal to moles. So that's what we're left at here. So 22 milliliters is my 0.3, so let's do that. And it has to be in liters, so 0.022 liters. Okay, I can do this math here. So this becomes 0.0022 moles. That's how many moles of hydroxide that is delivered by the burette to the moles here. Oh, what do we have here, party people? We don't have enough what? Well, how much moles were dropped? Okay, how many moles were dropped of base? Well, it is far less, 0.0022 moles. Now, you can write a stoich table if you want, but it's just that simple. Compare those two moles. Well, clearly, this is a driven reaction, and every single hydroxide is going to react with the ammonium. So it's a 1-to-1, so clearly I'm going to take away most of it, but how much is remaining? 0.0005 moles of what? Okay, of ammonium ions are available. Now if you don't see that, okay, and I know most of you do, so I'm going to waste your time because I want to make sure you can see that, you know, write a little stoich table. Now stoich tables take what? Take moles. And so what did I say here? We had how much? We had 0.027. Hey, put it right there. 0.0027. Hydroxide, we said at 22 milliliters is 0.0022. 0.0022. And of course these guys are 0. We don't care about the water because it's a liquid. And so how's this going to go? Well, if you do your stoich table and figure out limiting reagent, the hydroxide's limiting. So it's going to be minus 0.0022. This will be minus 0.0022. And this will be plus 0.0022. That's important that you see that. That is much what? Conjugate acid is lost. It's exactly how much is gained. Why? Because it's a 1-to-1 ratio. And so this goes to 0. This goes to what we just did. 0.0027 minus 0.0022 is 0.0025. I'm sorry, 0.5. And this, of course, is 0.0022. All right, now let me just make sure I write this clear because I know I'm apt to make some mistakes here. So party people, okay, and people that aren't party people, hey, it's okay. Those are important values. What did I just solve for in the Stoic table? Moles of remaining acid, and of course moles of conjugate base that we have to consider in this system. Why? Because weak acid, relatively stronger conjugate base, that can what? Yank H pluses in ionized water and affect the pH. Now, here's the cool part for 3. All right? Instead of converting these to a molarity, doing a equilibrium problem and figuring out the pH, all we need is the Henderson-Hasse block. Okay? And let's go do that. And what is the Henderson-Hasse block? It's given to you in your reference table or reference table. I'm going to go with, I don't know, black here. And it's what? The pH equals the pKa plus the log of the conjugate what? Base, the A negative, over the Ha, which is the conjugate acid. Now a little trick here is that, well, Mr. Grodsky, you just solved for moles. Don't I have to go to molarity? Well, I could. Okay, but I would have to get the molarity of those guys at equilibrium, okay, and I have to do an equilibrium problem. So the fast thing to do here is to actually just use the moles. You say, well, why can I do that? Because, well, isn't this bracket represents molarity? Moles over liter is equal to what? Moles over liter. And you should be able to recognize from basic canceling that you're going to, oh, Christmas, you're going to cancel off, yes, I guess I meant that, off your liters, and it's really mole over mole, because the volume of these concentrations are in the same beaker, okay? And of course, to get the volume, we'd have to add the what? The 22 milliliters plus, that was added, plus the 25. Remember, in here, it's 25 milliliters. Okay? So in any case, the fastest way is throw your moles in there. Okay? So what do we have? 0.005, that's for the conjugate acid, that's my Ha. So 0.005. I can do this. Not the green. Well, I can do that in green. Why not? 0.0005. And what was the conjugate base? 0.002. And notice there's a lot more conjugate base. Of course there is, because we're in this position here. As we've used up most of the acid going this way, we've created a lot more conjugate base. That should make sense to you. 0.002. So let's go there. 0.002. All right. 0.0022, I should say. Okay. Now we already know what the pKa is because we solved for that on the what? Second point, and that is 9.4. So I'm going to get rid of that and write 9.4. Okay. So let's do the math. 0.0022 divided by 0.0005, and if you notice you get 4.4. We're going to find the log of that, second answer, and I get from this expression right here 0.643, and I'm going to add that, don't forget to add, to 9.4. So plus 9.4, and what do I have? Approximately 10. My pH should be 10 at that position. And of course, it's not perfect. We're a little above 10, but we're pretty close. There's the 10. All right? So there's my thing there. And again, we had to do some stoichiometry to figure out from the driven reaction how much of the conjugate what? How much of the conjugate acid was remaining, because we didn't do what? We didn't completely neutralize it. There's some moles remaining. And more importantly, how much base, conjugate base, has been formed. Okay? Cool. Last point. And one of the easiest points is the final pH. Now what am I after? I'm after an H plus ion concentration. But what do I recognize? This line, these lines are going up. So I recognize the fact that my final pH, as I keep saying, you know, this levelsing out. If I was to add liters upon liters of the base I used, okay, you can notice that this is going to finally reach, or try to get to the original concentration of the base. Never quite gets there, it's the limit to that, but boy, you can get close over time. So in any case, enough said. What's the final pH? Well, everyone's got to realize that, and let's make another color here. Everyone's got to realize that from this position right here, this position in my graph, once I get to the equivalence point, essentially we consider that to be pure water. Now it's not perfect, but any extra that we add at the equivalence point is the concentration of the hydroxide. We're going to add extra hydroxide. Now, we just figured out at point 3 that we're going to lose most of it. And of course, at this point, this will be 0.2 as we add what? 27 milliliters, which equals exactly the 27.0027 moles. So this will be equal to the acid at this point. But after this point, this is going to be a greater value that will exceed this value. This is the limit of what's already in the beaker. So at this position here and beyond, the final concentration is what extra hydroxide did you add to the water? Because we're going to consider that to be pure water. So how much extra did we add? So if I look at my chart here, I got 27 and I have 50. All right, and let's go back to a color here. So 50. So how much extra base that I add beyond the equivalence point? And so 50 minus 27 and 3, and so what do you get here? We get 13? Yeah. All right, so 13, no, 23, my bad. So we get 20, I'm doing it by hand, why? 23. This is 4. All right, so 23 milliliters, okay, 23 extra milliliters, okay, is added. So what do I do with that? We've been down this road before. If I've got 23 milliliters, which is really what? 0.023 liters, don't I know the concentration of my base? It's 0.10. So I take the molarity, 0.10. Boy, I'm asking to make mistakes here. 0.10. So the molarity times the volume gives me the moles. So I've added 23 milliliters extra, 0.023 liters extra. How many moles extra into water? So party people, what we do is you times it by 0.1. Molarity times volume gives you moles for the millionth time. It's a fast way here. So 0.0023 moles of what? Hydroxide added. What are we looking for? We're looking for the pH. What can we get from the POH? The pH. But in order to get the POH, we need the molarity. What is the volume? It is not 0.023. In the beaker, as we've added, okay, all of what was ever in the beaker, in the burette into the beaker, as we added more base, the volume got bigger. But at this position here, party people, how much volume's in the beaker now? When we've added 50 total milliliters of base into my beaker, and we started out with 25, well, what's the total volume now? So we have 25 plus 50 milliliters. We had 25 of the acid originally, and we added 50 from the burette for a total of 75 milliliters in my beaker. So my new concentration, or to get the concentration, okay, what I'm going to do is divide by, all right, not 75 milliliters, but 0.075. Don't forget, molarity is moles over liters. So take out our calculator. Let's go find this. 0.0023 divided by 0.075. And what I get is 0.03067, and that represents the concentration of the hydroxide. Great. In that beaker. Let's go find the POH. Negative log that sucker. So negative log, second answer. And what I get is 1.51. I'm going to take 14 minus that. And there my pH is 12.4. So by finding the POH and then doing what? 14 minus the POH, I get my pH, which I get to be 12.5. All right, now I don't know where that is, but let's see how close I got. So this is 12, and if I look, hey, pretty darn close. 12.5 is like right here, so a pretty good, okay, verification there. And there's your 5 points, okay, in a nutshell or in a classroom with me with a video. All right, and again, 3 different equations, 3 different ways, at least a lot going on, I get it, but hopefully getting some momentum here. If you can do every one of these 5 points, then you can solve any acid-base problem presented. What I'm introducing today, though, is that we can create a buffer, and we'll see this as we partly titrate. Okay, question or point number 3 can be anywhere here to answer, and the best way is the Henderson-Hasselbalch. Okay, hope that helped.